Greetings all. Now that we've learned about the Earth-Sun relationship, we understand how the sun's energy, basically we understand when and where the sun's energy reaches the Earth's atmosphere. So now we're going to take a closer look at the sun's energy and what happens when it reaches our atmosphere before it actually reaches the surface of the Earth, and how that energy interacts with our atmosphere. So I want to start off with talking about forms of energy transfer. And the one that we've been talking about, solar energy, is radiation. So remember when we were talking about insolation as being incoming solar radiation? Yes. The answer would be yes. Radiation is just one way that energy can be transferred. And it's transferred in waves, like you see in this image here. And we'll talk a little bit more about that image in a moment. And what's cool about radiation is that it doesn't require a medium to be transferred. So it can transfer through outer space, through nothing basically, and anything that has a temperature, including ourselves, including the sun, including the earth, including the chair or the couch or the bed that you're sitting on right now, will emit radiation. So it emits energy through radiation. So we're going to talk about radiation, but before we do that, I want to just briefly talk about the other forms of energy transfer. And that is convection, conduction, and this isn't always talked about, but we're going to also touch on advection as the movement transfer of energy, and we'll also talk about latent heat, but we won't talk about latent heat just yet. Okay, so we have radiation, convection, conduction. I think one of the easiest ways to actually talk about these different forms here, these are the three primary ones that you'll probably be familiar with that are talked about the most. Radiation, so we understand that as the transfer of heat. We can look at these three components of energy transfer that happen when you are boiling a pot of water. So let's look at that. So let's say we're boiling a pot of water and we put it on over a flame. So here's your flame. Okay, so the flame is transferring heat through actually radiation. That radiation reaches the bottom of the pan here, and it starts to excite the molecules. So as you put energy into those molecules, they'll begin to vibrate and get excited. And as they vibrate, they also pass on those vibrations to the molecules that are touching them. So just like you can feel, if you put your hand on a train track, you can feel the train coming through the vibrations. This is the way that energy is transferred too. That form of energy transfer is called conduction. Conduct energy, okay? That conduction, that vibration can actually move through various metals very easily. And if you might have experience, depending on the material that your pot and handle are made out of, that the pot handle can also get very hot, even though it's not in contact with the fire, the flame that it's over. That is heat that's being transferred, or energy that's being transferred through conduction. So the same thing happens on the inside of this pot. As the molecules get excited, it passes that energy through, and then the water that's in contact now with the inside of the pot that has also heated up starts to heat up through conduction also. So that water that's just in contact with the the bottom, the inside of the pot, begins to heat up. Those molecules become excited. But here's the thing about water and air. Water and air are fluids. So that means that the molecules are not rigidly attached to each other like we think of in a solid. So the solid, it's not the molecules that are moving to transfer the energy. The molecules stay in place, but they vibrate, and those vibrations pass through the molecules. So that's how the energy is passed. Now, when you start to heat up a fluid where the molecules aren't rigidly attached to each other, like water, like air, those excited molecules begin to move about and mix around, right? Because they're kind of free to move. And as they become more and more excited, what happens is the water or the air begins to expand because those little molecules are going all over the place. They're super excited. So they begin to expand, and the density becomes, the density decreases, and that makes the water or the air that is heated and less dense more buoyant. So that means it becomes lighter and will tend to rise. Whereas the water or the air that is cooler and the molecules aren't moving around so much, that tends to be more dense and therefore heavier per unit area, and it tends to sink. So what you get there is the mixing of molecules, which is referred to as convection. Convection. So convection, compared to conduction, conduction is the transfer of energy through the vibrating molecules. From molecule to molecule, the energy is transferred. Convection occurs when the molecules themselves move around and mix and transfer that energy that way. So this warm energy and warm water here rises, the cooler water sinks and begins to heat up again because it's in contact with that hot surface. And you have this mixing of water or this mixing of air that transfers energy. So that's convection. We're going to get to advection and latent heat later, but I just wanted to cover those three different ways that energy is transferred for now. Okay, let's go back to this other page and take a look at this image here. I'm going to increase it. Okay, so I mentioned that the sun's energy, and actually anything with a temperature, radiates energy in the form of radiation. And radiation is transferred in energy through the electromagnetic spectrum. So this is an image here of the electromagnetic spectrum, and the wavelengths will be related to the temperature at which objects radiate their most of their energy. So there's a couple components to this image here that's really cool I want to point out. One is here, this temperature thermometer. Okay, it has Kelvin and Celsius. We're going to talk about temperature soon. And this is basically, this is hot, hotter over here. This is a squiggly line, not a negative. Okay, so it's about 10 million degrees Celsius. 9,000 degrees Celsius, and then we go minus 173, minus 272. So this is kind of absolute zero, which is something that has no temperature, so it's not radiating. So this is cooler over here. So what I want you guys to notice is that the hotter something is, the shorter the wavelength. And the cooler something is, the longer the wavelength. And when I say wavelength, this is what I mean. So if we have a wave like this, the wavelength is going to be measured either from crest to crest or from trough to trough down here, and they should be the same. So